everyone, welcome to the manufacturing processes class. In the previous video we introduced for the machining operation, we discussed the fundamentals of these operations and we discussed the conventional methods of machining. We discussed the turning operation, the drilling, the shaping and the milling operation, and we discussed their operating principle, how they were already working. And we discussed some of the essential aspects that should be considered or known about these different manufacturing methods as machining operations. And we said that in the machining process we should have a tool, and this tool, it should be with a specific with certain specifications, like it should have sharp edge to be strong enough to cut in the workpiece to end up with a chip. And this is the essential thing of performing any machining operation, that we have to form a chip. So we're gonna continue here on this topic, and we're gonna demonstrate some fundamental concepts and things related to the machining operations. All right, so now let us move to the another topic here, is the cutting tool classification. We said that we discussed the different cutting operation, and we said that there are some essential requirements to perform a machining operation. That we should have a tool, and this tool should be with a sharp edge, and it should include some specific angles, right? And then we discussed the different tool that would be used for the milling operation, the tool that would be used for the drilling operation, which is the twisted drill, but we didn't discuss the tool that is basically used for the lathe machine, which is the single point cutting tool. But generally speaking, we can classify tools depending on the count of the cutting edges, how many cutting edge that the tool is already having. Like for example, we do have single point cutting tool, and for this single point cutting tool like this one, it has only one cutting edge or one cutting point, and it is one dominant cutting edge basically is used for this type of tool. But in the multiple cutting tool or cutting edge tool, it means that you do have more than one cutting edge, like the case of the milling operation. This is the cutter of the milling operation. It has multiple cutting edges. This is one cutting edge, and you do have another cutting edge, and so on. Like in the twisted drill, how many cutting edges? You would have two. So that's why the twisted drill, it is classified as multiple cutting edge tool. But if it is only one cutting edge, so it will be classified as single point cutting edge. Single point cutting edge, like the one that is used for the turning operation. Also the tool that is used for the shaping operation, there is a single point cutting edge, right? But the tool that is used for milling, drilling, grinding, it is multiple cutting edge operation. In this one, the point is usually rounded, and there is a nose. Like there is a nose, which in this one, this is the point and this is the cutting edge. So there should be a nose here, and this is a secondary cutting edge. But this is the essential one. This is it is not the essential cutting edge. This is the essential cutting edge that we have. So that's why it is single point cutting tool. And this is the nose that we're already talking about, that we do have a point. So that's why this tool, this is the one that is used for the lathe machine. This is the one that is used for the lathe machine. It is named as the single point cutting tool. But in the multiple edge, motion relative to the workpiece to achieve is achieved by rotation. And most of the multiple cutting edge tools, that the rotation, the cutting, it should be done by the rotation of the workpiece, of the cutter or the tool, to expose the material or the workpiece to the multiple edges, because we're already having multiple edge. So to use these edges, we have to give rotation to the tool to expose the workpiece to these multiple edges. But in this one, it depends on the operation. But basically speaking, the difference that this is single edge, this is multiple edge, like the case of turning operation and drilling and milling operation, right? Now let us focus on the nomenclature or this geometry of the single point cutting tool, especially the one that is used with the lathe machine, right? It is commonly known for this course to understand the geometry of this cutting tool, and know the difference between and the objective and the function of all of these angles. So this tool, the geometry would be complicated somehow, but let us understand this one by one. So basically we do have multiple faces. We do have, this is a flank face, this is flank face, and this is the or flank surface, This is the top rack surface. This is this face of the tool. Let us call this one also face or the top rack. This is the rack surface of the top rack surface of the tool. And there is another flank surface which should be the other surface which is not seen from here. This is the another flank surface of the tool itself. And this is the nose, which is the nose radius, or this nose, which is just a little bit curved, and it is not just a point. It has a little bit small curvature, very small curvature, to initiate the start, to initiate the cutting, as the same concept of the chisel edge and the twisted drill. In the meanwhile, it should be very small to allow for the penetration of the tool inside the workpiece. And this is going to be the main cutting edge that we already talking about here, right? But these surfaces, the flank surfaces, in addition to the top rack surfaces, they already inclined surfaces. They are not straight surfaces. So like this one is already inclined in this direction. This flank surface also is inclined with a certain direction. But let us talk here about the top rack surface. The top rack surface, it is inclined in this way. Let me just add these things here so it's gonna be clear. As you can see, like there is like kind of inclination in this direction to this surface to allow for the easy removal of the chip, and we're gonna discuss this point. So these are the different projected views of this single point cutting tool. This is, if we consider this is the front view, this is with the American system of the presentation of the drawing. If this is the front view, and this is going to be the side view, and this is going to be the top view of the tool itself. So in the front view, we're going to have the front. This would be named as the front rack angle or the back rack angle, which should be the angle between the top rack face of the tool and the this line that it should be perpendicular to the workpiece, because you should have a workpiece surface here. There should be a workpiece. So this should be the perpendicular to the workpiece surface as we defined the rack angle before. This is the front rack angle, and this is the flank surface. This is the flank surface of the tool, and this is the tangent to the workpiece surface. So we're gonna end up with this angle between the tangent to the workpiece surface and the flank surface of the tool. This is gonna give us the end clearance angle, or the front clearance angle, or just the clearance angle of this tool from the side. But in addition to the front rack angle, we do have another rack angle, which is the side rack angle. As I mentioned, that this surface, it is not a straight surface, it is inclined surface from the side. So that's why it is not straight like this one. No, and instead it is inclined with an angle. This angle is a side rack angle, and this angle is important to allow for the removal, for the quick removal of the chip over the workpiece surface. Because during the turning operation, for example, this is the workpiece surface. So we should have here chip. There would be a chip that is gonna be removed over the chip. This is gonna be assumed that this is the chip that is going to be sliding over the surface of the tool itself, right? So if instead of having the chip sliding over the entire surface, in case that we made this surface a straight surface like this case, so the chip is going to slide over the entire surface. And instead we just give another rack angle, another inclination to the surface, so to have the chip going in this direction. So the contact surface, or the contact area between the chip and the tool, becomes more lower, or more smaller area, which will eliminate the amount of heat that is going to generate because of the sliding of the chip over the workpiece. And as we mentioned, one of the resources of heat generation is the sliding motion of the chip over the tool itself. So the surface over which the chip is going to slide, this is the top rack surface, and we would like to minimize the contact between the top rack surface and the chip as much as we can. So that's why we are achieving two inclinations, one in the front, one in the side. The same thing, this clearance angle, it is needed to eliminate the rubbing or the friction between the tool and the workpiece. So, but if we don't have this friction, definitely we're gonna end up with more heat that shall be generated. So to allow for, or to eliminate this friction, also to allow for the for removing the heat through the cutting fluid, or just by opening a gap for the cutting fluid to reach to the nose, we have to do this inclination to this flank and the other flank from the side. So that's why we do have two different clearance angles, one in the front, one in the side, which is this, like this is the other flank, this is the flank surface from the side. From the side here, it is not vertical like in this way, and instead it is inclined with an angle. This is the side clearance angle. Even from the top view, we'd have some angles here. This is definitely is gonna be the same side cutting edge angle. This is the side cutting edge angle, and this is the nose angle, because this is the nose itself, this is the nose, and you're gonna have here another angle which is front cutting edge angle. So these two cutting edge angles and this angle, they do define the geometry of the final product. These angles mainly depend on the geometry of the final product, and or in other words, they basically define the geometry of the obtained surface. They depend on these two angles. But the important angles, as I mentioned, are the front angle, the clearance angle, the side drag angle, and the side clearance angle. So again, the drag angles are used for the easy removal of the chip. The clearance angles are used for eliminating the friction between the tool and the workpiece and allow for the heat dissipation by applying the cutting fluid to the workpiece. This is also another representation of the same geometry. So to assist you to represent or to understand or to draw this geometry, basically we start from the front view. It is very simple, like you do have this is the body or the base or the shank of the tool itself, and this is the top rack face, and this is the clearance or the flank face. It would be straight or it would be with two different angles, it depends, but we do have like two like relief angle here, like two clearance angle. Relief or clearance is the same, but you can consider that we just do have one angle, which is this end or front clearance angle. We do have the back rack angle or the front rack angle, and this one it should be like square in this way in case that we don't have any inclinations. But instead of having this one as a square, should be the shank, this is gonna be the nose, and from this one, this to back face, it should be like horizontal, right? But instead we just making it inclined to minimize the contact area between the chip and the top rack face of the tool. So that's why we are applying this side angle. In addition, the flank, it should be also inclined to allow for another relief or another clearance from the side. So this is a side clearance or relief angle. Also from the top, we do have cutting edge angle. This is this is the side cutting edge angle. This is the front or the end cutting edge, and we do have the nose here, and this definitely is gonna be the top rack face. This surface is the top rack face of the tool, and this is three-dimensional representation of the same tool. So this is the tool that is commonly used for the cutting, for the turning operation, and these are some text, like explanation about these cutting edges or cutting angle that we already defined. And this tool, basically this is known as the tool signature. Like what distinguish one tool from the other tool is these numbers and their order. Like for example, this tool, it has back rack angle or the front rack angle is 0. This one has a side rack angle of 7 and 6 degrees as end relief angle, side relief angle, end cutting angle, and so on. So this number indicate the angles in addition to the nose radius is the last number here. Like for example, if you buy a tool, if you decided to buy a tool, so what are the specifications of this tool, of this single bone cutting tool that you are seeking? These are the specifications. These are the signatures. This is what distinguish one tool from another tool. One single bone cutting tool from another single bone cutting tool. Make sense? Now let us move to another topic, which is the cutting tool material. So since we are talking about machining operation, we said that the tool, it should be with a sharp edge. It should include some angles like the top rack angle and the clearance angles. And we discussed the importance of these angles. What else? What is that should be required to having a tool that would be used for machining? That the material should be made of a special material. the work part or the work piece that you're gonna machine, it would be made of any material. So we don't care about the material of the work part as much as we care about the material of the tool. The tool should be made of a special material, a strong material, a high strength material to achieve the machining process. But in addition, there is an essential thing that this material will include, that the material should have the capability to withstand the high temperature or the high heat that shall be generated during the machining operation. We said in the machining operation there is a direct contact between the tool and the workpiece, and we do have 3 or 2 main resources of generating heat. The chip breakage or the chip formation, this would expose some heat in addition to the friction between the tool and the workpiece, or the friction between the tool and the chip. So there is friction as a source of heat, there is chip breakage as another source of heat. So it means that we end up with a very huge amount of heat, so we have to use a material, or the tool should be made of a material that it should be special to withstand this high temperature that is going to generate during the machining operation. So that's why these are the essential requirements of the material that can be used as a tool for a machining operation. So these are the cutting tool material specifications or properties. Like it should have a high red hardness or hot hardness. So hot hardness or red hardness, what does it mean? It means that the material should have the ability to retain its hardness at high temperature. We may have a material with high hardness. If you remember from the start of this class, we define hardness as the ability of the material to withstand the indentation of other objects to its surfaces. So I would bring a material with a high hardness and make the tool from this high hardness material, but unfortunately this material probably won't gonna have the capability or the ability to retain or to keep or to save its hardness for a high temperature, at high temperature level. It means that as we heat the material, this material is going to lose its hardness very quick, right? So this material is not preferred as a tool. It is a strong material, high hardness material, yes, but it is not preferred. Why? Because it has low red hardness. We need high red hardness or hot hardness. It means that this is the ability of the material to retain its hardness at high temperature. This is different than just hardness. As I mentioned, how long in terms of temperature, up to which temperature that the material can maintain its hardness or lose its hardness. What is the maximum temperature level at which the material can lose its hardness? If it is high, it means that this is a good material and it can be used as a cutting tool for the machining operation. Also, it should have high wear resistance. Wear resistance means that it enables the cutting tool to retain its shape and cutting efficiency for a longer time. So we're gonna call it a name as the tool life. The tool life, it is how long that you can use this tool without resharpening, like the knife at home. The knife at home, you have to resharpen the knife after a while, right? So the period from which you bought the knife itself till the first time that you resharpen the tool, or till you resharpen the tool, or the resharpen the tool resharpening for the knife, this is the knife lifetime. This is the lifetime for this tool, right? So how long it will be used? It would be used in terms of time, in terms of number of machining operation, how long it's gonna live without resharpening. This is the tool life. And we need to make these tools from a material with a high wear resistance. Also, the toughness of the material, it should be high, which its ability to resist the shocks and impact during the interrupted cuts. There are some of the during the machining operation, probably we may end up with some interrupted cut, like you got this interrupted cutting. Like you may cut then stop, cut then stop. This is interrupted cut. This would result in some impact and shock loading. And the impact load, it is higher than the gradually applied load. So that's why we have to make the material from a material, the tool from a material with a high toughness, high wear resistance, and high rad resistance. These are the essential required properties of the cutting tool. So that's why we would have some materials which are recommended for as cutting tool for making cutting tools, like the carbon tool steel. If you remember, we discussed the steel is Fe plus carbon, right? So the carbon tool steel, that this is steel with different percents of the carbon that already forming the material. It is the low carbon steel possesses good toughness and shock resistance, but the high carbon steel is recommended over the low carbon steel for tools. And this one is mainly used for the tool that would be used for the manual cutting, for the hand cutting, not for the machine. But it would be used for some sewing machines and so on. But it is not very common for the machine tools themselves to this tool, because this is the lowest price, and this is the weakest them all in terms of for making tools. The material that is better than the carbon steel is the high speed steel. And high speed steel, we got the name because it has ability to withstand hardness, to work at very high temperatures up to 600 degrees Celsius. It means that it can retain its hardness at high temperature levels. This is the high speed steel. And basically the temperature generated or the heat generated depends on the speed. As we increasing the speed of the cutting motion or the speed of the machining operation, it means that we are going to generate more heat, and the temperature of the tool can be increasing. So that's why the carbon steel, it is recommended to be used for low speed cutting, but for high speed cuttings we have to use a better material like the high speed steel. So that's why we got the name high speed. It means that it is recommended for making tools that would be used for machining at high speed or high cutting speed. So that's why we got the name as high speed steel, which is carbon plus any other like tungsten and other chromium and other materials to give the material ability to attain its hardness at high temperature. So that's why we can increase the cutting speed. The cobalt, cobalt alloys, it is also one of the recommended material that would be used for as tools, and it would be steel. We would include cobalt to the steel as well as one of the alloying elements. But here it is mainly made of cobalt in addition to other material. It is mainly used for machining cast iron, alloy steel, non-ferrous metals, and super alloys, and also it can work at speed levels very similar to the high-speed steel. But the cemented carbides and the ceramic tools, they are more expensive tools because they are more stronger materials. These materials can be used for making good tools that can withstand or attain their hardness at higher temperature level, even higher than the high speed steel or the cobalt. And that's why they're gonna be used at very high cutting speed, the ceramic and the cemented carbide tools. The most expensive tool ever is the diamond, because this is the strongest material that we would have, and that's why the diamond tool, it should be used for special work pieces in case that the work piece is very tough work piece, and it can attain its hardness at very levels of high temperature and high speeds, right? So for example, if we represented like a schematic representation of as a comparison between these different types of materials in terms of their ability, and here you could consider that this is the cutting speed, this is the cutting speed. So this is how this material would be related to the cutting speed and the hardness. In the meanwhile, this is like the hardness. Assume that this vertical axis, this is the hardness of the material. So, and let us assume that this level, this is the minimum level below which we cannot accept this material as a tool. This is the minimum level of hardness. This is the minimum hardness level. Okay, so it means that if the material has been moved below this line, it means that this material lost, or the hardness of this material has been lost. This means that there is no hardness for this material and the material became very weak. So if the weakest material, the cheapest material ever is the carbon tool steel. The carbon tool steel, it has good hardness at room temperature. This is the room temperature at zero velocity or speed, at zero cutting speed. And as we move, the temperature definitely is going to increase as we increase the cutting speed. Make sense? So at room temperature, at zero speed, with no machining, it has the carbon steel, it has high hardness, but unfortunately it loses its hardness very quick. As we increase the speed, the cutting speed, the temperature is going to decrease, and at around 1 degree Celsius, 150 degrees Celsius, is going to lose its hardness very quick. This is the carbon steel. This is the carbon steel. This is the bad thing of the carbon steel. That's why it is not recommended as a tool. As you can see, the high speed steel, it has lower hardness at room temperature than the carbon steel. But the good thing of the high speed steel, that it can live for a longer period. It can attain or keep its hardness high at higher temperature levels for longer speeds. This is the high speed steel. This is the high speed steel. Although it has lower hardness at room temperature, but the good thing of the high speed steel, that it can keep its hardness for a longer time. That's why it is pricey, more pricey than the carbon steel. As you can see, the cemented and the ceramics, this is the carbides, and these are the ceramics tools. They are tools with very high hardness, and they barely lose their hardness, and it means that they can be used for very high temperature levels and very high cutting speeds. And the thing that should be located on the top is definitely the diamond. So this graphs gives like a comparison between these different materials according to their ability, or according to their red hardness properties and their abilities to attain hardness for longer or higher temperature level. And this is the essential requirement for a material that would be used for as a cutting tool. Although we can make these tools from carbides or ceramic or high-speed steels, and this material, they do have ability to withstand or keep their hardness for high temperature and speed levels. Although that this material would be weird and it should be resharpened after a while. As we said, that any cutting edge from multiple use, it should be resharpened, like the knife at home. So why we are doing resharpening, it means that there is wear already happening to this tool, and we do have two different mechanisms of the tool wearing, which are the crater wear and the flank wear. The crater wear, simply, it is located on the top rack face of the workpiece. This is the crater wear. This is the rack face. This is the rack face, and remember that the rack face, this is the face over which the chip is going to slide. So that's why the crater wear, it is mainly formed because of the sliding motion of the chip, which is very hot, over the workpiece surface. So this will result in heating the surface of the workpiece of the tool very high. I'm sorry, this is the rack face. This is the face over which the chip is sliding over the tool, right? And because the chip, it is very hot, the surface of the crater face, the rank face of the tool, it will be heated so much, and it will lose its hardness somehow, or decrease its hardness somehow. And after the multiple use, this crater wear is going to be formed, right? So the crater wear is mainly formed because of what? Because of the chip sliding, or the sliding of the hot chip over the tool surface. Which surface? The rack face, or the rack surface of the tool. This is the crater wear. But the flank wear, it is located over the flank surface, the side surface of the tool, and it is mainly because of the friction between the tool and the workpiece. But the friction, the wear that produces because of the sliding of the chip over the rack face, this is the crater wear. The flank wear, it is located over the flank surface, and it is mainly produced because of the friction between the workpiece and the tool itself. Make sense? And because of these wears, when they reach to certain levels and certain values, we have to do resharpening to this tool. Otherwise, we're gonna end up with products with very bad surfaces if we use this weird tool. Make sense? Another thing that we should understand about the machining operation is the machinability. What does it mean, machinability? It is how easy we can perform the machining operation. This is the machinability of the machining operation. And the machinability, it depends on so many factors. It is not just one factor that would enhance the machinability or would badly affect the machinability. So simply machinability, it is a measure of how easy if the machining operation can be done or can be performed. And there are so many factors, including the workpiece material. How the workpiece material would affect the machinability. If the material that is going to be machined is a soft material, so it means that we have a good machinability. It means that this material can be easily machined. But if the workpiece material, it is a very hard material, so we have to take precautions, and this material, we're gonna spend time in machining this material, or in other words, machining this material, it is not easy. It is challenging, and that's why the machinability of this hard material, it is very low machinability. But soft material, workpiece material, they do have very good or excellent machinability. The same thing, the tool material and geometry. The tool itself that you are using, you are using a tool that is made of a weak material, so you have to take precautions while you're already doing machining, and you have to use a cutting fluid. It means that the machinability using this tool, it is very low. But if you're already using a very good tool with very good geometry, with very sharp cutting edge, with very high strength material and red hardness material, it means that the machinability using this tool, it will be enhanced. There is excellent, so we can easily perform the machining operation. Also, the tool wear and tool life. What is the level of tool wear that the tool already having? How long this tool would be used without resharpening? This is the tool life. If the tool can have a longer tool life, it means that this tool can enhance the machinability, or we're gonna have a good machinability. The required surface finish. Are you just need rough surface, or do you need surface finish? Surface finishing for or producing products with good surface finish, it means that you have to pay more. This is costly. To finish the surface, you have to do one more operation after the rough phase. So we do like one pass or one machining operation, rough surface, to end up with the rough surface of the product. Then to finish the surface, you have to repeat the process again using another tool to perform the finishing. Like the case of reaming in the drilling operation, as we discussed. We said that we open the hole using a twister drill. Then to finish the whole surface, we have to use a reamer. So we have to pay more. So that's why if we are intended to have finished surface, it means that the machinability will be low. But if we are not interested in the surface finish or the level of the surface finish, so it is good machinability. Also, what are the required dimensional accuracy? Do you need to achieve high accuracy? Achieving the accuracy, you have to take precautions. It's gonna take time. It's gonna affect the machinability. It means that the machinability is gonna be low. Also, the machining cost. Is it costly or not? Also, the cutting condition and the cutting fluid. Are you using cutting fluid or not? If we are using cutting fluid, we can increase the cutting speed, we can increase the cutting cut. So it means that we don't worry about the temperature or the increase in the temperature due to the heat generation, because anyway we're gonna use the cutting fluid. It means that the machinability, it is enhanced. We do have machinability, better machinability. Also, the quality and the rigidity of the machine tool. Are the tool that you're already using is a new tool? I'm talking about the machine. How effective is the machine? Is it a good machine, or is it a used machine, bad machine with bad conditions? So this definitely will affect the machinability. In addition to the required machining forces and power, how much of power and energy needed to perform this machining operation. If we need higher power, it means that the machinability is low. If we need low power, it means that the machinability is gonna be high. It means that we can easily machine. So simply machinability is how easy we can perform the machining operation with lower cost, with lower effort, with lower precautions, kind of. Okay. So that's why also we discussed the cutting fluid. We said that this cutting fluid is important to get rid of the heat generated, and we discussed the two resources of the heat generation. These two resources, one is due to the breakage of the chip, the second one is due to the friction, that whatever friction between the chip and the top rack face of the tool, or the workpiece and the flank face of the tool itself, right? So, and the fluid that would be used for as a cutting fluid to get rid of the heat, it should have some properties that it should be of lower cost, that the reduction, or yeah, the importance. No, here we are discussing this is the, yes, this is the importance and the advantage of using a cutting fluid. If we are using cutting fluid, the cost of the tool will be reducing. It means that because the tool wheel will be reducing, the tool life longer, it means that the tool can live longer, it can be used multiple times. It means that the cost of the machining operation is going to be lower, and the cost of the tool will be lower if we're already using a cutting fluid. It means that you can like saving and like keeping your tool in a good condition if you're already using a cutting fluid. Also, it increases the speed of production, so we can finish the work very quick, and this will reduce the heat also, because it reduces the heat and the friction, so higher cutting speed can be applied. Also, it can be used for reducing the labor cost, because what does it mean labor cost? Because this is the cost of the hour, how long that depend on the hours, worked hours of the operator. There is some guy who's gonna use this machine and who's gonna operate this material. So this labor who already using and operating the machine, he is getting paid per hour, right? So instead of wasting time working and doing the machining operation with no cutting fluid, and you have to take precautions and you have to take rest and give rest to the tool to be cooled down. If you're already using instantaneously a cutting fluid, you can finish the job very quick, and in this case you're gonna save some cost which related to the labor cost as well. Tool lives longer and require less regrinding and less downtime, reducing cost per part in terms of the labor cost. Also, reduction of the power cost, because the friction is going to reduce, and the friction, it is further force, more force. If we do have high friction, it means that we're gonna require more power and more machining force to cut the chip. So that's why the using the cutting fluid definitely will reduce the friction, and it will save more cost in terms of the power. These are some of the characteristics to have a good cutting fluid, that it should be having good cooling capacity. It means that it can absorb the highest amount of heat as much as the fluid can. Also good lubricating capabilities or qualities, like it should, the lubricant action from the cutting fluid is needed to eliminate or minimize the friction, but the cooling action, it is required to absorb the heat. So the cutting fluid do two things: eliminate the friction because of its lubricating characteristics. In addition, it absorbs the heat that generated during the machining operation because of its high heat capacity, that it can absorb more heat. Also, it should have low viscosity to be fluid, because the viscosity, if it is very viscous, so it won't gonna be fluid through the pipes of the machine to fit into the machining zone. So it should be of a lower viscosity. Also, it should be should have good stability. It means that long life. It means that many of the cutting fluid, we are reusing them. We are pouring fluid, and this fluid is already collected back again into a pool, and we are using some like grids and meshes to clean it from the chip, and then we already using it one more time, so it can be reused. Also reused rust resistance. It should have ability to resist, to not do any to avoid the formation of oxides over the metal. Since we're already dealing with metal, so the rust can be easily formed, so it should be made of chemical materials to avoid the rusting formation. Also, it should include non-toxic materials, so we won't gonna badly affect the guy who's already operating and the laborers. Also transparent, it means that you can see through it, because it will be filling over the machining zone. So the operator should be observing all the time what's going on at the tool tip. So it should be transparent so I can see through the fluid, the cutting edge itself during the cutting operation. Non-flammable, it means that it cannot be burned, or like these are some of the required properties of a good cutting fluid. Okay. This part basically it is related to the mechanics of the cutting operation, but I won't gonna cover this part because this basically it is covered in the theory of metal cutting that we discuss the concept, and it should be discussed with more detail in a separate course about the formation of the chip and the requirement and the forces that generated during the cutting operation. But the thing that I'd like to mention here are the basic types of the chip during the operation. We are talking about this chip. This is the chip part, right? So what are the different forms and different types of the chip that we would end up or form or would be formed during a machining operation? Generally, we have three main types of the chips. One is the discontinuous chip. We do have continuous chip. We do have continuous with built-up edge chip, which is commonly BUE, stands for built-up edge, and this is one of the not recommended cases of the chip. We are trying to avoid this type of chip, or we have to take precautions in case that we gonna have built-up edge, as I'm going to explain. The discontinuous, it means that the chip it can be easily broken down, as it is broken from the workpiece itself. Like this is the tool and this is the chip over the top rack face. Again, this is the top rack face. The face over which the chip is going to sliding. This is the top rack face of the tool, and this is the flank face of the tool. Right? This is the flank, and this is gonna be the top rack face, or just directly the rack face of the tool or surface. So the discontinuous chip is formed in case that the workpiece is a brittle material. This depends on the material type. If it is brittle, so we're gonna end up with discontinuous chip. It requires low cutting. It is produced at low cutting speed. If we're already performing the cutting operation at low cutting speed, it's gonna be obtained, especially in case that the workpiece is a brittle material. It also produces as large feed and depth of cut. So as we increase the depth of cut and the feed and decreasing the cutting speed, we're gonna end up with a rough surface of the workpiece. The workpiece will be rough surface. So the rough surface will be obtained as we decrease. If we're decreasing the cutting speed and increasing the feed and the depth of cut, we said that we do have three cutting conditions, which are the cutting speed and the feed and the depth of cut. So if we are increasing these two and decreasing the cutting speed, we're gonna end up with a rough surface of the workpiece. The produced surface will be rough, and the chip will be discontinuous, especially if the workpiece is brittle material. Okay, high tool chip friction, and this will result into a very high friction between the tool and the workpiece, or the chip and the workpiece and the tool, and that's why we have to use a cutting fluid for this one, and it is not recommended. But the continuous one, it is mainly produced in case that the workpiece is a ductile material, and especially in case that we're already performing the machining operation at very high speed, but low feed and low depth of cut. So for small feeds and depths, or low feeds and depths of cut, so in this case we're gonna end up with super finish. This is smooth surface of the workpiece. This is known as finished surface. Finished, it means that it is machined. Like surface, it means that this surface is it is not a rough surface. And this happened as we increasing the speed and decreasing the feed and the depth of cut, and the tool edge is sharp, and low tool chip friction will be result in this case. So that's why it is recommended over the discontinuous chip. But in some cases for the continuous chip, especially in case that the material is very ductile material, that we would end up with build-up edge. What does it mean, build-up edge? Build-up edge, it means that part of the chip will be completely melted. The chip should be in the solid state and sliding over the surface of the tool, right? But for some cases, because of the very high temperature and the friction at the tool tip, we would end up with some build-up edges like these cases. And these edges are not recommended. We have to avoid them, right? And this basically happens, as I mentioned, in case that the tool is very ductile material, and it happens when we are doing low and medium cutting speeds, and the tool friction is very high to make part of the chip will be melted and adhered and sticking to the top break face of the tool. And if this happens, this would result in bad sliding, or would overcome the sliding of the chip over the top rack face and will increase the friction, and hence will increase the heat more, so more build-up edges will be formed and the process continues, right? So this is very bad, and this is not recommended, and we have to avoid the formation of the build-up edges during the machining operation. And the main reason behind the build-up edge formation is the melt of particles, some of the chip particles or portion of the chip, because of the very high heat at the cutting edge. This will make the chip to be adhering and sticking to the surface, to the top rack surface of the workpiece, and this will badly affect the quality of the obtained surface and will badly affect the tool, and it would break the tool and damage the tool as well. So the build-up edges forms then breaks off quickly. Cyclically, it means that the process already is repeated. We do have one of the things to avoid the formation of the build-up edge. The build-up edge is formed only in case that we have continuous chip. And this basically what happened for the ductile material. And when we perform the cutting operation at low or medium cutting speed. But if we do have a ductile material and we are doing the cutting operation at high cutting speeds, so there is no possibility, or the build-up edge is not likely to be formed, or it won't gonna be formed as long as we are attaining high cutting speed. But for some reason, we may be required to perform the cutting operation at low and medium speed, so there is a possibility of forming the build-up edge. To get rid of forming the build-up edge, we have to break down the continuous chip, because the continuous chip will be on contact with the surface, so this would allow for more particle to sticking to the rack face. So what we basically do, we do like a curve, a groove beyond the cutting edge within the tool, just forming this groove within the tool. This will allow the chip to be just moving inside the groove, and while it comes out, it will break down. So this is like chip breaker. We form chip breaker, something to break the chip beyond the cutting edge by forming a groove. So what is a chip breaker? This is forming a groove beyond the cutting edge with the purpose of breaking down the continuous chip to avoid the formation of the build-up edge. This is the objective of the chip breaker, and these are the different types of the chips that would be formed during the machining operation. As I said, we won't gonna discuss these force terms, and we just gonna focus on the we won't gonna go deeply through this mechanics in terms of the forces and so on, but we just gonna consider next how we can calculate the machining time, the metal removal rate for the different machining operation that we discussed, the turning operation, the milling operation, the drilling, and the shaping operation. So that's it for this part. What we discussed so far, we discussed what does it mean machining. We discussed the different the traditional machining operation, the most common machining operation, the turning, milling, drilling, and shaping operation. Then we discussed some other things related to the different tools that would be used for machining. We'd have single point cutting tool, we'd have multiple point cutting tool. Also, we discussed some other concepts relating to the machinability, how we would enhance the machinability, the cutting fluid. We discussed the different types of the chips. The remaining part of this machining processing is to know how we can calculate the machining time and the metal removal rate. The machining time is the time needed to machine or to finish a machining operation. Also, the amount of metal that is going to be removed per unit time, how much it is. This what we are going to cover in the next video. But that's it for this video and for this part. And in the next video, we're gonna discuss the meta removal rate and the machining time. So thank you and see you in the next video.